in our example of glass and phosphor, if you take the first row average, so we're going to need to look back at this table and pick out this number and take the difference between this number and that number, we'll get a so-called fitted effect of glass number 1. So I make this comparison. If I make a comparison between this number and that number, I'll get a so-called fitted main effect for glass number 2. So main effect of glass number 1 is 289.44 minus 262.22, and that's 27.22, and the units here are microamps. Fitted effect for glass number 2 is 235 minus 262.22, and that's minus 27.22 microamps. If I make the effects, or compute the fitted effects for the 3 phosphors, phosphor number 1 average is 260, and if I subtract from that 262.22, I'm going to get minus 2.22. If I take the third column average, that is 273.33, and if I subtract from that 262.22, I'm going to get 11.11, and if I take the third column average, 253.33, and subtract 262.22, I get minus 8.88, and units of these are still the original units, and those are the quote-unquote fitted effects of the fitted main effects of factor A and factor B. Now, what do these things tell us? In the first place, look at the signs here. Factor A fitted effect, its sign is positive. Factor B fitted effect, its sign is negative. That's a reflection of this obvious fact that glass number 1 means are above glass number 2 means. So the sign on A1 and A2 tells us that current requirements for glass 1 are above current requirements for glass 2. If we look at the signs on the B's, this picture should tell us that B number 2 should have a positive, should be bigger than B number 1 and B number 3, because means for phosphor 2 are above means for phosphor 3, and sure enough, this guy is positive, whereas the other 2 guys are negative. What else can we see looking at those numbers? If we look at the magnitudes of the A main effects in comparison to the magnitudes of the B main effects, on the whole, these guys are bigger, okay, in magnitude than these. Well, that again is obvious from the appearance of this plot. That is, the gap between the glasses is bigger than the up or down movement as I go left to right on this glass on this interaction plot. So those are reasonable quantifications of what we see visually on this picture. Now you could say to me, well, gee, we already see that visually, why do we need numerical summaries of that? One answer to that is that we're going to need those numerical summaries if we're going to talk about statistical significance or detectability of these things. Is we'd like some way of knowing whether these are more than just random noise, these effects that we're calculating. And the other answer to that is we can make these kinds of pictures where there's only a couple of factors, start to have 3 or 4 or 5 or 10 or 20 factors. We're going to be hard pressed to make and interpret graphics, whereas we will be able to make and compute quantities like these AIs and BJs that we've made here, that we can then interpret data from a system where there are not just 2 knobs but many knobs. So you got to walk before you can run, and so we're making calculations here for simple two-way things that will generalize to many factors, not just 2 factors. One other thing to say about these computations: it's no accident that when I add those 2 guys up, they add to 0. Similarly, although it's not quite so obvious, but it is true that when I add these 3 guys up, I get 0. That is, the main effects for any factor, it's just a consequence of the way that we've defined them, that fitted effects fitted main effects for any factor sum to 0.